Welcome, everybody. I'm glad you're all here for this presentation about black holes and dark matter. It's something everybody's a little bit afraid of, but Dr. Kenefick is going to tell you why you don't have to be afraid of it. Just a couple of things before he goes on. There's a Pathfinder on that back table listing some items in our collection about space. And there's some evaluation forms. So when you leave here today, if you would please just fill one of those out, drop it in the box. It really does help us with programming. And also, there are some eclipse glasses on the back table for people here at the program. There's an eclipse on October 14th and then one on April 8th. So you can kind of be prepared for that. And our presenter today, as I said, is Dr. Daniel Kenefick. He's a professor of physics at the University of Arkansas. He received his PhD in physics from Caltech in 1997. And after a postdoc in Cardiff, Wales, he joined the faculty at Caltech, where he worked as an editor at the Einstein Papers Project. You can elaborate on that tonight, right?
Sure.
He has been in Fayetteville since 2003. In 2007, he published a book on the history of gravitational waves called Traveling at the Speed of Thought. He is also the co-author of an Einstein Encyclopedia. Most recently, he's the author of No Shadow of a Doubt, the 1919 eclipse that confirmed Einstein's theory of relativity. His physics research focuses on supermassive black holes at the centers of galaxies, both as possible generators of gravitational waves and for their role in galaxy structure and evolution. So I don't know anything about this. I'm very excited to learn, and I'm going to turn it over. Please help me welcome Daniel Kenefick.
Thank you, Kelly. Thank you for inviting me. I'm going to mention right away that my wife, who is, as we like to say, the real astronomer in the family, would like to have been here, but in the end, she had to go off on a trip. The good news is that we're going to be talking about things that you cannot see. So really, it belongs in my bailiwick. I'm interested in things that you can't see. Not only do I never look through a telescope, I can't make them work. And that's why Kelly mentioned my interest in history of science. And that includes a little bit of the history of astronomy. And so I was once asked to be on a TV show. And when they interviewed me, they said, "How would you like to be identified?" And I was a little puzzled. And they said, "Well, you know, we don't want to necessarily put assistant professor at the University of Arkansas because it looks a bit long on the screen. Can we just call you an astronomer?" And I said, "Sure, you can call me whatever you like." What I didn't realize, I only realized once I saw the show, is all the other sensible people who were on the shows put below their name, author of by my book, which I totally forgot to do. I'm sure my publisher wouldn't have been very pleased. So my wife, however, was highly amused at the word astronomer, and after that she took to introducing me by saying, "This is my husband. He's not really an astronomer, but he does play one on TV." So today you're getting not the real astronomer, but on the other hand, we're going to be talking about things that you can't see anyway, so it's not too big of a loss. I decided not to do any slides, first of all, because you can't see black holes and dark matter, so there aren't so many pretty pictures to show you. Also, I thought maybe it would help encourage you to ask questions. In that vein, normally when you're dealing with physics, of course, it's foolish to imagine that people have questions to ask you. I did meet a very distinguished, not so long ago, very distinguished historian of science, physicist, who said to me, "Well, you know, you can tell how people are interested in black holes because if you're in a taxi to the airport and you don't want to talk, when the driver says, 'What do you do for a living?' you say, 'I'm a physicist.'" End of conversation. If, on the other hand, you're feeling chatty, just say, "I study black holes." And all of a sudden, you'll be bombarded with questions. So I'm hoping that that effect will work on you guys. I'm only going to begin by pointing out that what brings black holes and dark matter together is gravity. And that's what I study, is gravitational theory. So Einstein's general relativity, and of course, we still use Newton's theory of gravity as well, and when the occasion demands. If we think about, let me find one of these pens. If we think about a universe before there were galaxies, there were, of course, all the same amounts of molecules and atoms, as long as we don't go back too far, that there are today, but they probably must have been pretty distributed evenly in what must have been a pretty rarefied space. So we can imagine the little molecules just spread around here. But of course, Newton tells us, his universal theory of gravity says that the way gravity works is every little particle that has mass, and they all have mass, attracts every other little particle. So all of the little lonely molecules are attracting all of the other little lonely molecules. And that means they all move towards each other very slowly at first. Because, for instance, I would like to think of myself as a magnetic kind of a personality, somebody who has a little gravity to them, and maybe is an attractive person. But let's be honest here. Right now, none of you are falling for me in the actual gravitational sense. You are not all falling towards me. So what do you think? How much of a force am I gravitationally exerting upon you at the moment? Would anyone care to estimate? Clearly it's not newtons. Right? Micronewtons is what, if the most sensitive spaceships that are out there, the ones that we hope will eventually detect gravitational waves, they have what are called micronewton thrusters. So think about that, a millionth of a newton. So like a newton would be, you know, I could give a little push and that's probably about a newton. So a millionth of that turns out to actually be quite hard to make a thruster that gives that little of a push. Right? And yet that's still enormous compared to what's going on here. So it takes, in an almost literal sense, forever for these guys to start glacially slowly moving towards each other. But the good news is, once they do get a little bit closer, what happens to their gravitational attraction? Once you're closer, you can actually see each other and you think, that molecule is pretty cute looking. Let's get a little closer again, okay? And so gradually, still with glacial slowness, the cloud pulls itself together, and this is what's called gravitational collapse. And it is the way, since the 18th century, this idea has been proposed. One of the first people actually was the philosopher Immanuel Kant, as the thing that makes us happen, right? It hasn't dominated the stage for the whole time, partly because it took a long time to work out the details. We're not going to go into all the details. Now, all I'm going to say is that eventually, of course, you begin to have what is almost like a real little cloud. And then for subtle reasons, once that's happened, of course, things start to actually crash into each other. And that results in heating. Because when you fall, right, here in Fayetteville, we know all about potential energy, right? When you go down a hill, you gain energy. The potential energy that you had at the top of the hill is converted into kinetic energy if you freewheel down on your bike or your skateboard. And if you hit something at the bottom, the kinetic energy gets converted into heat and also some sound as you moan, other things like that. So the heat, this cloud starts to get hotter. And as a result of the loss of energy, but you have to still conserve your angular momentum, the cloud flattens out, which is kind of a thing that often happens to spinning things. And so you end up with a disc-shaped object. Although at the center, where most of the mass is concentrated, because after all, that's where all the gravity is ultimately pulling things, is to the center, you have a bulge. So this is the disk of an emergent galaxy, and here's the bulge. I want you to keep in mind, and this is the main point of saying this, how much denser the bulge is than the disk. We live, as you may know, way out in the disk. This is my opportunity. Usually in class, I would start singing at this point. Does everybody know the Monty Python Galaxy song? Okay, well, maybe we'll sing it at some point. The bulge, at any rate, is the place where you have many more stars. Isaac Asimov wrote a very famous science fiction story back in the 60s, 70s called Nightfall, which is about a planet in the bulge of the galaxy. So, yes, why was I mentioning Monty Python? We're 30,000 light years from galactic central point, right? So we're a long way from the center. We're out here. But if you were in the center, the night sky would look very different because there are so many more stars there. Here, the night sky is really actually quite unimpressive. There's a famous story about, I was recently in Amsterdam. My daughter wanted to go to the Van Gogh Museum, so we went. They don't have the famous painting Starry Night there. But the story goes that Van Gogh told his fellow artists, I'm going to paint the night sky. And they said, Vincent, you do know it's impossible to paint in the dark, don't you? And he discovered they were right. You can't see the canvas. If you put a light on the canvas, now you can't see the stars because they're so dim that if our dark sight is removed at all, we lose sight of them. Wouldn't be a problem on the planet that Isaac Asimov wrote about. There are lots and lots of bright stars quite close. So the sky would be positively ablaze with stars. So I want you to think that the center of the galaxy is very, very, very dense. What does that mean? That means gravity is very intense there too. So both dark matter and black holes are going to come out of our consideration of gravitational collapse. And in particular, the big question would be, why did it stop? After all, if the whole point was that it started slow but picked up speed, why did it stop? That's a big question. But you also may have questions of your own, so I'm going to pause at this point because you may want to jump in.
Well, is it stopped? I mean,
Well, something would have to stop it, right? So Newton tells us that you don't stop anything from moving without a force. They used to think, of course, that stopping was a very natural thing to do. But that's only because we live on the Earth, where there's always something in our way, right? And so even if it's not directly in our way, friction, for instance, will slow me down. So we're used to things stopping, but out in space they don't, right? If you get moving in space, then you'll keep going, which is why the astronauts are tethered to their vehicle when they leave it, right? Because once you're moving away, there's no way to come back. So if there has to be a force to stop it, what do you think? Any candidates for the force?
dark matter?
Dark matter. So let's think about dark matter. One of the important things to remember about dark matter is not quite, but almost the only way that it interacts is in fact gravitation. That's the main thing that distinguishes dark matter from regular matter. There probably is some dark matter in the room right now, if we knew more about it. We're not guaranteed that it's in the room, but the current thinking is that probably there's dark matter in the room, but we don't notice it. We can't see it because it doesn't emit any light, but it does more than that. In addition to not emitting light, it doesn't actually interact electromagnetically at all. It is totally standoffish. Maybe you know, I know that nowadays lots of grade school kids know this, which I always find very impressive. It's always interesting as a physicist to find out, if you write a physics test and you have a question that 100% of this, I'm thinking now especially one of those big physics classes where there's dozens or even hundreds of students, if you write a question that 100% of the students get right, well, that was something that everybody knew when they came into the class, because I can tell you, it never happens that everybody was listening when you said something. 80% of people is about the maximum you're going to get if you're an incredibly good teacher. Okay, so if it's 100%, everybody knows this. So here's something that maybe everybody knows now, and that is that when I push off of something like that, it's not really what we kind of think, oh, it's because matter, 2 bits of matter somehow can't be in the same place at the same time. I'm mostly empty space, and so is this podium. What's happening is that the electrons in the outer parts of my atoms, having a negative charge, don't like being close to the electrons in the outer part of the atoms here, and it's the electric repulsion of our electrons that's keeping us apart. So here on the Earth, we can definitely say, oh, and so dark matter. First, we'll come back to that in a second. Dark matter. Dark matter doesn't have any of that. So that means the dark matter in this room is just floating right through me. And I don't feel it because it doesn't bounce off me. And the only way it interacts is gravitationally, but you will remember, I hope, about how sucky my gravitational attraction is. So unfortunately, even when the dark matter goes right through me, my gravity is incapable of really slowing it down much at all. And it just flies on through, and then probably out of the room, and then probably off the planet Earth and off back into space, and another dark matter particle comes into view. So it is this mysterious stuff. The trouble is, because it doesn't tend to clump, I clump because the same kinds of forces, these contact forces, are also capable of chemically bonding my molecules together to create a human. Dark matter, as far as we would guess that there are no dark matter humans out there because they don't clump together. And that's bad for gravity because although I am puny in gravitational terms, the Earth is reasonably impressive if you can get a really big object. The sun does a fantastic job, gravitationally speaking. So you have to make big things. And actually, the way we make big things is by electronic forces, typically. And dark matter doesn't have those. So the interesting thing is that dark matter, although we only can sense it gravitationally, there is another sense in which it's also a little bit unimpressive gravitationally. We're going to come back in a while to what it really does. But it turns out that it probably has almost no role to play in this critical matter of stopping things. We do know that the Earth here has stopped luckily, shrinking, right? It's not collapsing any further. And that's because I remember I mentioned that the Earth, though it has much more impressive gravity than me, is still basically pretty puny in the gravity stakes. So what's going on here is that the electron contact forces of the rocks and the stones is more than sufficient to stop the Earth from collapsing any further. That's not, however, true of the sun. We're not going to go into the sun too much today because it's not really our focus. But stars are actually massive enough to crush themselves down pretty small. The reason that they don't is that when you crush things together, the atoms and the nuclei get very, very close. And something happens that's kind of, I guess, in the popular news at the moment, because we had a movie that sort of discussed this. What happens at the center of the star when you squeeze things very close together? Fusion, that's right. The nuclei actually get squished together to fuse. The movie Oppenheimer is, of course, about the atomic bomb. That, of course, is not fusion. But you may have noticed that there was one guy in there, Edward Teller, who kept muttering about a bigger bomb, a hydrogen bomb, and that is where you do fusion. Fusion releases an enormous amount of energy, and that light produced by that energy is trying to get out of the sun, which is very hot, and it's a giant plasma. And a plasma is unusual because the electrons there floating freely do a lot of deflecting light rays. So what stops the sun from collapsing, rather remarkably, which was only figured out a century ago by an English astrophysicist called Arthur Stanley Eddington, is the light pressure, the radiation pressure of the light trying to get out. Now, this sounds pretty incredible. For instance, I've never ever had a class say, Dr. Kenefick. I always tell them to call me Dan, but students are traditionalists to a fault, and it makes them nervous to address most of them. So they always call me Dr. Kenefick. Dr. Kenefick, could you turn the lights off, because my head's a little sore today, and the pressure is too much from the radiation. Never happened. As a matter of fact, it's difficult in any laboratory on Earth to measure the pressure of light. Okay? If you're science fiction buffs, you may know that the sun is a bit different. It produces so much light that it's possible to think of making a spaceship by having a solar sail, which is pushed by the radiation pressure of the light from the sun. That's how much the light the sun puts out, though admittedly it has to be a very big sail. But deep inside the sun, the light is so intense, and because there's so much bouncing back and forth, you know how long it takes light to get to the Earth from the sun? 8 minutes. Very good, 8 minutes. How long does it take the light to get from the center, where it was born, to the surface of the sun? Any guesses? Short, long? I forget. I didn't come prepared for this. It's at least in the hundreds of thousands of years, but I think it may be in the millions of years. Okay, so that's funny. Is it going slower there? No, it's still going at the speed of light, which only takes 8 minutes to cover them tens of millions of miles from the sun to the Earth. Why does it take so long? It's because you're going, it's like Lenin, the founder of the Soviet Union, used to say, 2 steps forward, comrades, 1 step back. That's how you get out of the sun, right? You start going up, you strike an electron and you get bounced back, and then you strike another electron and you start going up again. And that way, even at the speed of light, it takes that long to go a relatively short distance. While you're doing all of that bouncing, remember Newton's third law is every action has an equal and opposite reaction. While the light is being pushed back, it's pushing the gas up. That is what stops the sun from collapsing any further. Bad news, eventually the sun's going to run out of nuclear fuel, and then it will resume collapsing again. The good news is not for a few billion years. That's always the toughest part. Kelly mentioned how scary these things are. I find with kids, the bit about the sun eventually dying is the scariest part. I do try to say, that is, we're talking 10 billion years or something of that order. But nevertheless, once it's been brought up, it's hard to get it out of your mind. Okay, so what will happen to the sun when it collapses? I bet some people know this. Yes. It might become a black hole.
The stronger fusion will make it swell up.
That's right.
The right time.
That's right. That's right. For a while, it'll start to fuse more complicated molecules. Right now, it's just fusing hydrogen. And that will make for a hotter core. And paradoxically, the hotter core heating up the outer gas will actually make the sun expand. So the core gets smaller, but the sun gets bigger. It might get to be so big that it swallows the Earth. It'll be red, though, because when the surface is so far from the center, it cools a little compared to the center. And so when it cools, it gets redder. I know this is backwards because we're used to thinking of red as the hot color, because if I heat up a poker in the fire, it glows red. The thing to remember is, from a physics point of view, what it was doing before was still glowing. It's just that our eyes can't see the radiation it was emitting. What kind of radiation was it emitting before? You need a certain special kind of goggle to see it. Infrared. So everything glows. It's just that our eyes only see it when it gets hot enough. And typically we're used to red being the thing that's hotter than what we are used to. But red is the coolest color of what our eyes can see. Stars can glow not only red, but like our star yellow, or even like a really hot star blue. And yes, we'll end up with a red giant phase. But then it will run out of that fuel, and then it will collapse again, and now we're in danger of black holes. But there is one possibility other than the black hole, two possibilities other than the black hole.
Brown dwarf?
And not a brown dwarf. A brown dwarf is what you get if you are a failed star. I know that it's common to talk about excellence in all things. I'm a little, I don't know, I get a little tired in the college of, excellence. Yeah, do we all have to be excellent? Whatever happened to just doing it? Just being good. My old advisor, who's now a Nobel Prize winner, so he's definitely excellent, Kip Thorne, he used to say that there was a Russian proverb, the perfect is the enemy of the good. It doesn't have to be perfect or excellent. Let's just do it, okay? A brown dwarf is a star that it's too big to be a planet, but it's not big enough to spark off nuclear fusion. So there's a mystery. Why does that not collapse? And the answer is something weird, which I'm going to say it, one of those bad moments in pedagogy where I'm going to say it, but I'm not really going to explain it. It's something called electron degeneracy pressure. Electron degeneracy pressure is what happens if we take all the molecules, this is the scary bit. Don't tell Kelly. I don't think she's listening right now. I'm going to scare you, okay? What happens if we do gravitational collapse on this room right now? All our atoms and molecules are going to get squeezed down until they essentially break. Right now, I've got a nucleus with the electrons going around orderly fashion, little orbits. Think of it like the planets, although it's a bit different. If I crush them down so I don't have orbits anymore, now I've got all those nuclei close together and the electrons trying to squeeze in between them. Turns out the electrons hate to be squeezed down like that. And the more you squeeze them down, the faster they jiggle around. And of course, anything that's jiggling around pretty quickly produces pressure. And that electron degeneracy pressure is the thing that stops a brown dwarf from collapsing, even though it doesn't have a nuclear furnace. And when the sun runs out of its nuclear furnace, it will collapse and also be held up by electron degeneracy pressure. But because it collapsed down pretty small, it will be much hotter than a brown dwarf. So what color will it be? If it's hot, it's going to be white. It's going to be white. Yeah, that's right. So it's going to be a white dwarf. A white dwarf is about the size of the Earth. Imagine taking most of the mass in the sun and squeezing it down to the size of the Earth. It's an incredible kind of an idea. It's incredibly dense matter. We don't have any matter on the Earth that's as dense as the matter in a white dwarf. However, you might think, okay, but if I squeezed it down, isn't the gravity greater? It sure is. If you were on the surface of a white dwarf, you would be literally squished as flat as a pancake. I'm definitely scaring everybody. Okay, but don't worry, you're nowhere near a white dwarf. You can't even get there. They're too far away. So you're going to be squished as flat as a pancake because your tissues just aren't strong enough to withstand that kind of gravity. So the white dwarf then is the endpoint for our sun. But suppose our sun had even more gravity, then it turns out that electron degeneracy pressure can't withstand that. And the upshot is that it gets squeezed down even further until it becomes a neutron star. And a neutron star is held up by neutron degeneracy pressure. Incidentally, if you've ever heard of, we haven't even gotten to black holes yet. This is the trouble about physics. There's always one little bit to explain on the way. Probably everybody's heard of supernova. But on the other hand, none of us have seen one. Why? Because in one of the most spectacular examples of historic bad luck, there were not one but two supernovas seen by the last great astronomers of the pre-telescope age, Tycho Brahe and Johannes Kepler. I hope you've heard of Tycho and Kepler. If not, definitely look them up. And then Galileo thought of pointing a telescope at the heavens, and the heavens suddenly sent, ooh, I better watch out, they might see my supernovas. So we haven't had a supernova in our galaxy for 400 years since we invented the telescope. The closest was the Magellanic Cloud in 1987, but you only get to see that if you live in the southern hemisphere. So basically nobody's seen one, but they're pretty spectacular. What happens is the star is collapsing. Now, gravitational collapse at that stage isn't slow anymore, right? Because now we've got incredibly intense gravity. Imagine the steepest, longest hill in the universe where you're really careening down it. And then all of a sudden, you hit the wall of the neutron degeneracy pressure. It's just like the electron degeneracy pressure, except it's neutrons. Neutrons are little subatomic particles that are inside the nucleus of the atom. That's such a hard wall, and you hit it so fast that it creates a titanic explosion. We can no longer say it's the most titanic explosion in the universe, because it turns out, boy, there's some pretty titanic explosions going on out there in the universe. But it is a pretty titanic explosion. To give you an idea, if I go back to the Monty Python song, our galaxy itself contains 100 billion stars. Okay, that's a lot of stars. That's a lot of stars. As a matter of fact, that's an underestimate. A supernova typically outshines all the other stars in its galaxy. So a supernova suddenly explodes with light that is more than 100 billion times that of a regular star. So that's why, if it does happen in our galaxy, we'll probably see it. But unfortunately, they're rare because few stars are big enough to make one happen. When it does happen, you'll have a neutron star. A neutron star is about the size of Fayetteville. The mass of a star squeezed down into the size of Fayetteville. When you get squished from standing on a neutron star, do not visit a neutron star. I don't recommend it. You will not be as flat as a pancake. Pancakes really aren't that flat compared to neutron stars. The tallest mountains on neutron stars are about 1 millimeter high. Where are the tallest mountains in our solar system? Oh, I got some planet experts here.
Is it on Mars?
Mars, yeah. Why would there be a bigger planet on Mars than there is on Earth? After all, everybody knows that Mars is a small planet. How come they get the big mountains? Yeah? The answer is that they've got less gravity. Their mountains weigh less. Why do our mountains not get much bigger than Everest? It's because if you have a mountain that big, its weight is so massive that it literally crushes the ground beneath it and it sinks down. On Mars, with its weaker gravity, you can have a bigger mountain. Anybody want to guess what the tallest mountains on neutron stars probably are? Based on calculations. How high? What's the size? What's the Everest of a neutron star?
1 millimeter?
1 millimeter, yes, exactly. That's right, 1 millimeter. So that's a mountain, and you're not as strong as a mountain, so you're going to be a lot flatter than that, right? You're just going to sink down into the, not a pleasant thought. Okay, that's neutron stars. We've got to come back to the black holes. What if we have a star that's so big, even neutron degeneracy pressure can't halt the gravitational collapse? The answer is, past that, there is nothing that can save you. The collapse goes on, as it were, forever. What does that mean, forever? It means two things. The first is, if you think about it in terms of what's going on with the star, it falls down and becomes what? A point, maybe? A singularity, people maybe heard this term. That takes all the mass and squeezes it down into a literal point. Quantum mechanics might make it vibrate back and forth. You'll sometimes hear people say that. Yeah, that's making a bit much of it, though, because it's going to vibrate back and forth on the Planck length. And that's something like 10 to the minus 45 meters. That's like 40 orders of magnitude smaller than the smallest thing we can measure. And we can measure some pretty small things. So it's a point. It's a crazy point, but it's a point. On the other hand, gravity has one really peculiar, funky aspect in Einstein's theory of gravity. That is, everybody's familiar with the GPS system, right? So the GPS system is that thing that tells you where you are. It's incredible. For those of us who are old enough to remember a time before it, there were lots of times when you had no idea where you were. Nowadays, everybody knows where they are all the time. When we visited, I'm from Ireland, we spent some time in my hometown at the harbor, and my daughter's very interested in the Titanic. My hometown was the last port of call for the Titanic, so we were looking up shipwrecks and things like that. And we noticed that there were loads of shipwrecks. There was even a place where you could go to see a plaque with every shipwreck around the harbor. And we noticed that at a certain point there stopped being shipwrecks. Not exactly GPS, but pretty close to it. Basically now, there's so much information that there's less chance that you're actually going to be in a shipwreck. So GPS is very interesting, very important. You probably know that, the key way that it tells you where you are is that your device sends a signal up to the satellite, and the satellite transponds with a signal. And you can tell where you are by the time that it takes the light. Remember, we knew that it takes light to get 8 minutes to get from the sun to the earth. So if you measure the time it takes light from get to one place to the other, then you can tell where that signal came from. And that means that both you, your device, and the satellite have to have a clock on board. Here's the funky thing. Einstein said, as long ago as a century, when he was one day, if there's time, I'll come back and tell you this story, but for now we're going to speed ahead so I don't lose the track. He was looking out the window of his workplace and he had a great idea. And the idea basically amounted to this. He decided that gravity can slow time. The original idea, this was Einstein, so there were quite a few important logical steps from the first idea to this. We'll come back to it if there's time. The key point was that he realized that gravity slows down time, which means that your clock in your GPS device or your phone is running slower than the clock on the satellite. And that has to be allowed for, or the system won't work. You won't know where you are at all. Right? The satellite will be, no, I think you're in Rogers. No, I'm pretty sure I'm in Fayetteville. When they actually sent the satellites up, some of the engineers said, that can't be right. I mean, I know Einstein's a smart guy and all, but there's no way the clocks are going to run differently up there than down here. And so they actually put a switch so that they could, if necessary, switch to the other way so things wouldn't go crazy. But it turned out Einstein was totally right. And GPS wouldn't work if he wasn't right. Okay, so if gravity slows time down, and a white dwarf and a neutron star even more, and a black hole even more have an incredibly strong gravity, then does time get slowed down there? Yes. And how much? A lot. The gravity at the singularity is essentially going to get infinite. So close to the singularity, there is a point called the event horizon in which all sorts of strange things happen. The most important of which we're going to come back to in a minute. But first of all, a key point is that at the event horizon, as seen by somebody out here with a clock that's not in a gravitational field, time stops. So seen from out here, the collapse of the black hole literally does take forever. Because as it collapses, it slows its own time. If there was a clock there falling with the gravitational collapse of the black hole, it would stop when it reached the event horizon. So we don't see anything ever fall through the event horizon. At one time, they used to call black holes frozen stars because of the idea that everything that ever fell into the black hole was still frozen, trapped like a fly in a spider's web, right on the edge of forever at the event horizon. You don't see it, though, for reasons we'll come back to in a minute. But that's the event horizon. It's a pretty spooky place. The other thing, of course, that's important about the event horizon is, not coincidentally, but it's a different factor. It's the point at which light cannot escape the black hole. When we think about gravity, we think, hopefully, if we're realistic, space-interested people, we think it's actually pretty tough to get off the Earth. It's even pretty tough to get off the moon. There are asteroids where it's not so hard. There are asteroids where it's so small and the gravity is so weak that I could jump off. That would be fun. I've always quite wanted to do that, although I don't know that I'm willing to travel all the way to the asteroid belt just for this exciting moment. But you're in there with your spacesuit and you give a big jump and you don't come down. You get slower and slower as gravity pulls on you, but it never quite slows you down. That speed at which gravity never quite succeeds in pulling you back, because although it's slowing you, you're getting that bit further away, and thus the gravity is weakening, and so it never quite succeeds. That is called the escape velocity. The escape velocity on an asteroid can be small enough that a human could leap off. The escape velocity on the Earth, unfortunately, is pretty high, which is why we need all these very, very powerful rockets to accelerate us off the Earth. What happens at the event horizon of a black hole is that the escape velocity is the speed of light. That means even light cannot escape from inside the black hole. That's why we call them black. That's part of why we call them black. But we do call them a hole. And this is actually where Mr. Oppenheimer, did anybody see the movie Oppenheimer? Some. It's a good movie, I recommend it. There's a moment in the movie where they're talking about black holes. They use the word just to flag this to us, though that's anachronistic. The word didn't get invented till later. It was Oppenheimer's work, though, that inspired the eventual term, because Oppenheimer was the first person to really ask this very difficult question. This question, why did it stop? People didn't ask that question for a long time. And the reason is we don't want to be scared. It's like Kelly said, right? It's a little bit terrifying to think of these things. And people literally, even the physicists, even the hardcore, tough-minded scientists, they just didn't think it. They didn't go there. Oppenheimer went there, and he said, yeah, if I think about gravitational collapse, once I go past this point, which later got called the event horizon, it had a different name then, I'll never get out. I'm stuck. So it's a hole in the sense that once you're in the hole, you can't get out of the hole. And it's black because even light can't get out, so you can't see what's in there. So it's literally black. Dark matter, of course, is a bit different. It's dark because it's not shining, right? Unlike most other things in the universe. The black hole could have lots of stuff that's capable of shining in there, but whatever light it makes, it can't get out. Why? Because just like, remember, I said on the asteroid I could float free, but I did already do it. I'm going to do it again just because I quite like jumping. If I jump, I come down again. Imagine if I shone my flashlight up and the light went up and then fell down again. That's what happens inside the black hole. Pretty crazy to think about. Okay, now I've been talking for a long time. Questions?
Does the light eventually run out in the black hole?
Well, we'll think about what happens again. We've got to be bold and keep thinking. I shone my flashlight up. The light goes up. It slows. It gets to zero speed. It comes back down again, and it keeps falling, and it keeps falling. And where does it end up? At the singularity. What happens to it there? We don't know. Why? Because we can never see it in singularity. They're always surrounded by this event horizon. You can't see it. Even if I go inside the event horizon, any light that was created by the singularity would not come up because the singularity's gravity is so strong. We'll come back to my next thought in a minute. I'll just answer your question as directly as I can. Yeah, so the light will just fall down. And so what happens if you have a flashlight inside a black hole? We're used to thinking of light expanding out from a light source in all directions. What will happen inside the black hole is the stuff that's pointed down will fall extra fast because it's going down and being pulled down by the gravity. And the stuff that was trying to go up will be pulled so hard that it goes down instead of going up. You had a question?
I think my question was answered, but is the singularity at the center of a black hole?
It is, yes. That's a great question. I didn't say that. So the original mass distribution, which is probably going to be a star for these purposes right now, the original mass distribution had a center of mass. That's a Newtonian concept, right? That's the point you get if you sort of average all the mass. And yes, by kind of an iron rule, that's going to be the point where everything ends up. So that's where the singularity is going to be.
Okay, surrounded by the event horizon.
That's right. Yeah. And the event horizon will be, it doesn't have to be a sphere, actually, interestingly enough, but it will be a roughly spherical shape around it. Yeah.
Is there going to be a difference between the smallest star that's possible, like the black hole made from the smallest possible amount of material versus the largest amount of material, or does it become immaterial because the gravity is just so dense?
Yes, that's a great question. The black hole still has all the mass there. Essentially, the way I would think of it as a relativist, as a gravitational physicist, is all that mass, which used to be the mass of the star and all that sort of stuff, has now been converted into just gravitational field energy. That's not a very meaningful phrase, maybe, to someone who's not a relativist. It's a different kind of object than it was before, but it has all the same mass that it had before. So if you make, let's say, let's say that you made a black hole out of it's just about what's needed to make a black hole, which might be about roughly 3 times the mass of the sun. So what we would say 3 solar masses. Well, then you'll have a 3 solar mass black hole. But let's say you make it out of 30 solar masses worth of stuff. Then you'll have one that's 30 solar masses. I'll go this one and then yeah.
All right, you're shining your light,
Yes.
it's escaping, or trying to escape.
Yes.
So it starts out faster and then slows down, and then as it comes back, does it speed back up?
That's a great question, very important question. It turns out that it's actually a little more subtle than what we would get from our Newtonian. That's the Newtonian picture we would have, and I did basically use that picture. It turns out that actually it's not really like that inside the black hole, and the reason is because of a peculiar feature of space-time.
Right.
Space-time is the entity that Einstein uses as the underpinning of his theory of gravity, and it's a pretty subtle concept. We're not really going to have time for me to go into any great length to it, but a pretty good way to think about the black hole is that you've punched a little hole in space-time, and now you've got a great river of space-time or a great flood of space-time flowing down into that. And you are just, the reason that you're moving so quickly is that you're being carried along with the river. Here's an interesting thing to think about. Let's imagine that we're going to go down into a black hole. Right? Okay, don't tell Kelly. Okay. We're going to fall into a black hole altogether, though, so it'll be fun together. Not really. We're going to go down into the black hole. We're going to do it. It's easy, right? Somewhere out there, not too far away, is a black hole. All we got to do is stop firing our engines, and we're going to fall into it. That's the way gravity works. They never switch it off, even after 5 o'clock, even at the weekends. It's always on. So we're going to be falling into it. We're going to accelerate the whole time. Again, that's the way gravity works, right? 9.8 meters per second every second, okay? And forget 9.8 meters per second. This is a black hole we're talking about. We're accelerating hard, okay? We're falling down, down, down from some great, considerable distance. What speed will we be going if we free fall from a far distance? What speed will we be going when we hit the event horizon?
Light years?
Yeah, we'll be going at the speed of light, precisely at the speed of light.
6,000 miles per second.
Yeah, that's right, 186,000 miles per second. That's how much accelerating we're going to do. We are going to be covering 186,000 miles every second. So that last bit we're going to cover in a split second. Right? We're going to hit the event horizon, and we're going to be moving at the speed of light. Once we go through the event horizon, we're still falling. We're going to accelerate past the speed of light. Now, if you know a little about relativity theory, you know that Einstein became famous for saying nobody can travel faster than the speed of light. So what the hell's going on? The answer is to think about it this way. Nobody travels faster than the speed of light, just in the same way. Let's say you're in the Buffalo and you fall out of your canoe and you're being swept down the Buffalo, maybe it's in flood, and somebody looking from the shoreline says, "We've got to save Harold, he's in the river," and then somebody else says, "Yeah, but he's going like 20 miles an hour down the river. I didn't know Harold could swim that fast." And he can't. It's just that the river is flowing that fast and he's in the river. You're in the river of space-time that is endlessly flowing down into this hole that was punctured in reality, and it's just carrying you along with it. You're not moving at the speed of light. You're not moving at all. That's the way Einstein thinks about gravity. You're just flowing with the river, and the river is now going faster than the speed of light inside the event horizon, and you go with it. So now think about the flashlight again in the context of this picture, which is more realistic. You're at the event horizon. You shine the flashlight. The light that was trying to go down is moving at the speed of light. And it's also, so let's, I need to rub everything out. Start over. Here. Okay, so here's the event horizon. I'm going to kind of draw it as a dashed line because, of course, you can't see it. It's just a point in space defined by certain mathematical attributes. Here's you with your flashlight, your light source. So you've got one photon that's trying to go downwards at speed c. C is the usual letter we use for the speed of light. But space-time is flowing downward at speed c. And the speed of light is its own speed, just like Harold in the river. It's your speed of swimming downstream. and the speed of the river going downstream. So at what speed, relative to the person standing here, see, it's not called relativity for nothing, at what speed is the light going down as they see it? 2c. Yeah, c plus c. C plus c is 2c. So that light is falling at a speed of 2c. The light that's trying to go up is trying to go up at speed c, and it's thinking, I'm going to bust out of here, guys. I can move at 186,000 miles per second. Don't worry, I'm going to go get help. Okay, but it's in a river that's going down at speed c, so what's its speed? 0. It's stuck. It's stuck on the event horizon. It never goes anywhere. That must be kind of cute to see a photon just sitting there. Right? Yeah, so it's stuck. It actually doesn't go anywhere at all.
So if I show my flashlight 1 millimeter above the event horizon, it will be going slower than the speed of light and then gain speed? Or what would happen if I'm just beyond when I shoot the flashlight away from the...
Yes, if we're just upon the event horizon. Okay, that's a great question. Harold, remember your question, please. I'm sorry that I'm not getting back to it. That is a great question. Okay, this guy is going to go up at speed c. Einstein's theory says that everybody measures the speed of light the same. So up here, far from the black hole, we're going to say that the light that we can see reaching us is going at the speed of light. So what is it that we see? If they thought it moved at speed c and we think it moves at speed c, there must be something we see that's different about this crazy guy that just barely escaped. The answer is easy to think about when we think about in terms of what happens to the astronauts in their spaceship when they get up. There's something different about them and their rocket ship than from when they started.
They're not like in the gravitational field, so they can just float around.
That's true, yeah, that's right. That's a very important one. We'll come back to that one. Another thing that's happened is they're out of fuel. They expended all their energy getting up there. So imagine how much energy this light photon lost in going from there to there. What happens when a light photon loses energy? According to Planck's law, it also loses its frequency, which means its color gets redder. So it's been red-shifted. It's now become a very long wavelength radio wave. That's the real reason. Remember I said that everybody, from the perspective of this guy, Kelly stayed behind bravely. Somebody has to, I mean, the library can't close, right? So we all went down. And when we got to the event horizon and did all these exciting experiments that we just talked about, Kelly looks down, and will she see us suspended on the event horizon? No, because the light that escapes, the last light that we sent just before we went to the event horizon, that got red-shifted to nothing. So the thing is that this poor photon, by the time he reaches us, is so low in energy that he's basically worthless. He thought he was going to escape, but it's like all those things, you know, when you escape out of the raging river, you're bloody tired. So you don't actually see all those frozen things. It really is a black hole.
There's lots of black holes out there, right?
Yes, we think so. Yeah.
And do they attract each other? And would a supermassive one exert more of an influence than a small one?
Absolutely would. Great question. You're moving things in my direction. Thank you, Harold. Yes. Black holes, we've already discussed, they come in different sizes. Okay. For instance, maybe as much as 30 times the mass of the sun. When LIGO, the gravitational wave detector, very exciting moment because I study gravitational waves. So for decades, gravitational waves was this crazy subject that bizarre people like me studied. Why was it strange to study it? First of all, people weren't entirely sure they were even real. And one thing we were all convinced about was that if they were real, they were too weak to detect. So what was the point? But nevertheless, we thought, well, they're cool. We studied them. People got crazy enough to try building detectors. And finally, in 2015, they were actually detected. The very first signal to be detected was from a binary black hole, because black holes still have all that gravity. If the star that created the black hole was in a binary star system, and there's a lot of binary star systems, then if the other one ended up being a black hole too, now you had a binary star system, now you've got a binary black hole. They're still moving around each other. And if they're close enough, as they hurtle around each other, they emit gravitational waves. The energy taken away by the gravitational waves comes from their orbital energy, so their orbit degenerates. They're drawn together, and eventually they crash into each other. And the last burst of gravitational waves when they crash into each other is pretty phenomenal. enough so that even though these things are incredibly hard to detect, we did successfully detect them. And it was, in fact, 2 black holes of a little more than 30 solar masses each that crashed into each other. Now we have a chance to do some basic math, right? The simple kind of math, not the hard math that Einstein does. If you had one of them, let's say, for the sake of argument, was, let's just say, 33 solar masses, and the other one was 32 solar masses. So what do you think was the mass of the new black hole? It's got to be a black hole when they merge, because if the gravity was strong enough to make it be a black hole beforehand, it's going to still be a black hole afterwards. 65 solar masses. That's clearly our budget here. Conservation of energy tells us that we must still have 65 solar mass worth of energy afterwards. But here's the kicker. As best we can measure the mass of the new black hole, and it's a bit iffy actually, but we're reasonably confident all the same, because we're physicists and we always try to be confident. We think that the black hole that was left when the 2 black holes crashed into each other and merged, 60 solar masses. So the question is, we now know there's 5 missing suns there. Where did they go? Energy release.
The gravity, like, used it as energies.
Yeah,
so,
that's
like,
right.
disappeared.
That's right. It's in the gravitational wave. The gravitational waves is a form of gravity that carries energy with it. Those gravitational waves had 5 solar masses worth of energy. So now, here's our chance to do some basic relativity. Everybody, I hope, I'm betting 100% can tell me one equation from relativity theory. E equal mc squared. That's right, that's right. Well, here's where you get to know what it means, and it means something big. Okay, what it says, what Einstein is saying, is that anything that has energy has mass. So light, which has energy, must have mass. That's what made him famous, right? He said, energy must have mass, light has energy, therefore it must have mass. Everybody at that time was thinking, no, light's not a material thing, so it isn't affected by gravity. And Einstein said, no, I think it is. And so they went to an eclipse, right? We're all interested in eclipses right now. I've got a whole book about this, if you're keen. It is, as one favorable reviewer put it, dense but readable. There's a lot in it, but still. Some good stories, but you know, some science. Okay, so he tells you light has mass. So it also can happen then that we can use the equation the other way, right? We can say, okay, how much energy is in the light? If there's 5 solar masses missing from the black holes, and that went into the gravitational waves, it's not light in this case, but gravitational waves are in some ways similar to light. How much energy do we have? Well, we're going to put in 5 solar masses. Anybody have any idea how big the mass of the sun is? Over 10 to the 30 kilograms. That's a 1 with 30 zeros after it, kilograms. That's a lot. 5 times that, then multiply that by the speed of light squared, 186,000 miles a second. Square that, you're going to have a lot of zeros. That's a lot of energy. Remember I said, so that was the total energy output by that cataclysmic collision. Remember I said that the supernova had as much light as the whole rest of its galaxy. All of that energy came out in not much more than microseconds. The last bit was pretty quick. During that split second, the total flux of energy from that system, that black hole crashing into itself, was more. So it outshone, but gravitational waves, we can't see them except with our expensive detector. It outshone every star in every galaxy in the universe. There was more energy coming out of the gravitational waves in that system than all the light from all the stars in the visible universe. So it's a pretty incredible amount of energy. Remember the whole idea of Oppenheimer's deadly toy, to use Sting's phrase, is that you're converting mass into energy. You take some of the mass that was in the plutonium in your bomb, a fraction, a percent, and it's not a very big, it's a few kilograms, and you convert that into radiant energy, and that blows away all those poor people in Hiroshima and Nagasaki. Now imagine that you take all the mass in 5 suns worth, and you convert that into energy. That's a lot of radiant energy. Okay, now I'm really, Kelly, sorry she ever invited me. However, I have some good news. Let's think about it. That's a lot of energy. That sounds very dangerous. But gravitational waves actually turns out they're very, very, very safe. If you were standing on a planet revolving around that binary star system at the moment where it smashed into create a black hole, that flux of gravitational waves would roll right by you. What do you think? How damaged would you be? This calculation I've actually kind of done. You'd be totally unharmed. Totally unharmed. All that the gravitational waves do is stretch space and time. So they would stretch you with it. Turns out space and time is incredibly rigid. It does not like being stretched. Okay? Right now there's gravitational waves going through me, but you can't tell because the amount by which I get stretched is so tiny we can't measure it. Even that close, 1 astronomical unit, the distance from the Earth to the Sun, away from that system with all that energy, all that would happen is your inner ear would probably be stretched enough so that you'd hear a little pop to tell you that it went by. So you'd be totally unharmed. The way to think about it is a laser is a pretty dangerous thing. A powerful laser, right? Hits you, burns you. But not if you're made of glass. If you're made of glass, you don't absorb it. It goes right through you. Now, admittedly, you have to be high-grade optical glass to be safe with a big laser like that. In gravitational wave terms, you are made of the highest grade optical glass imaginable. You do not absorb gravitational waves at all, hardly at all. So all that energy would just flow right through you, and you'd be totally unharmed. When we saw that signal, the big detector, which is in Louisiana, there's another one up in Washington State. We're not too far. I urge you, if you were down Louisiana way near Baton Rouge, to go to Livingston and visit. At least once a month, they usually have a visiting period. You can visit the detector. You can see it. It's incredible. They have a little science center there in addition to the tour of the facility. There's Louisiana. There's the big L-shaped LIGO detector. Where was the black hole? Well, of course, it was 1.3 billion light years that way. But it was also on the other side of the planet. The waves came right through the planet because they're not stopped at all. We're made of the purest glass to it. So that's one of the interesting things about gravitational waves. When we say we've got all sky coverage, we mean everything. It's not the Earth isn't in the way. We see 360 degrees, which is a little bit of a problem because when nowadays we're all excited, right? We're seeing, right now, LIGO is in 04, observing run 4. Every time they think they see one of these, they send out an alert to the astronomers to see if they could see the same thing with light. Right? But the astronomers have a problem, right? Because we may say to them, yeah, we just saw one. And they'll go, where? We're going to point our telescope the right way. We go, well, sort of over that way. That's a bit of a problem. But nevertheless, they're working on that. Okay, I forget what the question was. I hope I answered it.
So if the black holes, it's like a river with space-time energy flowing into it.
Yes.
Well, didn't Einstein say that you can't create or destroy energy, like conservation of energy? So how does that?
Well, when I talk about space-time, I'm talking about something that I'm saying doesn't have energy. It's just the substrate in which we all exist. Now, you're touching on a very important point here. It's not so clear that there's no energy in the mere vacuum of space. In fact, and I hesitate to say these words because it's going to cause confusion, that's what dark energy would be, the 0-point energy of the vacuum of space itself. Okay, so it has nothing to do with dark matter or black holes. It's a different thing. They should never have used the word dark there because that is confusing the hell out of everybody. I would call that something different. I would say that's the cosmological constant because it's more to do with cosmology than anything else. But at any rate, the key point is that it's going down, and the way I would think about it as a classically trained Einstein gravity person, that doesn't have energy. So I just think about that as being like the grid against which I measure everything. And then that grid keeps moving on me. Right, so that's the key point. Newton said, yeah, we think of space-time as like a big grid, and we can watch ourselves move. And Einstein said, actually, now that I look at it, that grid could be moving, which is a subtle point that maybe we shouldn't try to go into too much. But think of it as there's always going to be more bits of the grid it's not to be thought of as an energy thing. It's just a useful fiction for thinking about how the.
But isn't it finite, the universe? Or is it?
Oh, that's a big question, yeah. Almost certainly no, but possibly yes. Let me come back to that if there's time. But the most likely situation is that it is not finite, and that it's infinite, and that we can think we have as much grid, we have more grid than we can possibly conceive. Yeah. We had more questions there.
Well, I was just gonna say, where is that gravitational wave going if matter doesn't stop it?
Mm-hmm.
Is it
Yes,
going
that's a good
forever?
question. It's going forever to infinity and beyond. Yeah. Yeah, it is tricky to think about that. But yeah, I mean, the short answer is it just keeps rippling on out there. It's like thinking about it like a really, to gravitational waves. To everything else, the universe is this dynamic place full of collisions, and to gravitational waves, the universe is like the stillest pond you can imagine. And so those ripples are just going to ripple on out there. And there's no edge to the pond, and there's no departure from the stillness, and they just keep going.
Hopefully it's a good question. Spaghettification.
Oh, yes, yes, that's true. We have to talk about spaghettification. We might have to ask Kelly to leave the room for this part.
So does gravity cause that?
Yes, it does, right. So let's talk about that event horizon, because I did say, when I advertised that we were all going to go down there and do some experiments, I did say it's not a great idea. So let's just send me down and you guys can watch, okay? It's going to be fun. You're going to enjoy it. Okay, when I get close to the black hole, something interesting is going to happen to me. Everybody, I hope, knows about the tides and knows, I think, that gravity causes the tides. Why do we have tides? The answer is that the moon is up there, and the moon is pulling on us just as much, equally as hard, but in the opposite direction that we pull on it. Now, consider that we're not actually a singularity, we're an extended body. One bit of us at any given moment is closer to the moon, and that bit is being pulled harder. And the bit on the other side is being pulled less hard. And the upshot is that anything that isn't nailed down is pushed up a little bit on that side and a little bit the other way on that side. And so the sea has two big waves, one on either side of the planet. And those are the tides. So the Earth, which the water is the most visible, but even the body of the Earth is distorted a little bit, is stretched and squeezed in this direction by the tidal effect of the moon. The tidal effect of the moon is actually greater than the tidal effect of the sun. You may know that, maybe I won't go into the tides too much, but the sun contributes its own tidal effect, but the moon has a bigger tidal influence on us than the sun. Why, when the moon is so much smaller than the sun? The answer is that it's much closer, and so the relative distances between one end of the Earth and the other, one end of the Earth is actually pretty close to the moon, and the other end is actually relatively far away, whereas the sun is so far away that the size of the Earth doesn't matter as much compared to that distance. So, in other words, when you get close to something, tidal influences shoot up dramatically. When you get close to something as strong with gravity as the black hole, tidal effects get very intense. So now, as I fall towards the black hole, it's going to take me a little while, not very long, because I'm going to accelerate to near the speed of light. So quickly, what's going to happen to me as I fall towards the black hole? Faster and faster. But also, my feet are going to be accelerated much harder than my head if I fall feet first, which I recommend. Think about it. My feet are going to be falling away from me because they're going to be falling harder. My legs aren't made for that kind of stress. Okay, I am going to be actually stretched and pulled apart because my feet are just going to fall away from me. And so that's what's called spaghettification. It's a highly technical phrase in my field. And yes, you will be literally pulled apart as you reach the event horizon.
So gravity can harm you.
Definitely, yes. Yes, gravity can totally harm you. Yes, I would hate to say that gravity can't harm you. Dark matter, by the way, is pretty safe. We haven't even got to do dark matter because, when black holes and dark matter get together, black holes are the life and soul of the party, and dark matter is off in the corner, having an aperitif and hoping somebody's going to talk to it. Yeah. So, but yes, the gravity is definitely dangerous, and the tidal influences are the way it's going to get you.
How long can life survive in the universe? And can any life survive in a black hole?
Inside a black hole? Almost certainly not. That is a great question. Before I answer that question, which is a big one, I've got to go back to what Harold said earlier about the supermassive black holes. We talked about the 30 solar mass black holes, and I said we're now pretty convinced. That gravitational wave detection, which was awarded the Nobel Prize, that's what my advisor got the Nobel Prize for, and a couple of other guys. It really got the Nobel Prize for being the first detection of gravitational waves. That's a big deal, right? 100 years since Einstein came up with this idea, and everybody was saying, well, maybe they're real, but we'll certainly never see them. But it also proved the existence of black holes, because there's a perfect match between the theoretical calculations I do about what those gravitational waves look like coming from those black holes and what the detector saw. So that's pretty convincing evidence that Einstein's theory is right and that the prediction of black holes is right. Those two 30 solar mass black holes made a 60 solar mass black hole. So is that as big as they get? The answer, it turns out, is hell no. We have to now go back, I rubbed it out because it took me so long, to that bulge at the center of the galaxy. Remember the gravitational collapse of the galaxy? Why did that stop? The answer is that in some sense, our fall never stopped. Right now, we're falling towards the center of the galaxy. But we're falling towards the center of the galaxy in exactly the same way that the Earth is falling towards the sun. That is to say, we're orbiting the sun. The sun is pulling us towards it, but we're going fast enough to orbit it. Douglas Adams, author of The Hitchhiker's Guide to the Galaxy, said the secret of flying is to fall and miss. And he was dead right. That's what orbiting is, right? You fall and you miss. And that's what we're doing around the center of the galaxy. Let's see. We're orbiting. We're 30,000 light years from galactic central point. We go around every 200 million years. So we're in a big orbit, 250 million years or so, around the center of the galaxy. But in the center of the galaxy, the stars were so thick. Remember Asimov and Nightfall? The stars were so thick there that probably, we don't know for sure yet, we would love to know how this happened, but probably the stars were just so thick that they all crashed into each other and created a supermassive black hole. At the center of our galaxy, there is a big black hole. We can see stars going around it, and by measuring the way the stars orbit, we can use Newton and Einstein's theory to measure the mass of the black hole. And it is over 4 million times the mass of the sun. That's a big thing. That's a lot of gravity right there. So we know that galaxies from time to time merge together. If they each have a black hole, and we're now pretty convinced that they all do at the center, remember, at the very center we expect the black holes. When the galaxies merge, there's a crazy period, but eventually the two black holes will end up right in the middle again, and they'll probably be orbiting each other. And again, if they're close enough, then the gravitational waves take the energy away, they spiral in towards each other, and then eventually they crash. And boy, we'd love to detect that. That's what I'm waiting for. But the frequency of those waves is too low. As things get bigger, the frequencies get low. We can't detect those with an Earth-based detector because the ground is just too unsteady. All those earthquakes, all that stuff. So we got to go into space. So we're trying to fly a detector called LISA, and it is tremendous excitement. I don't have time to tell you the entire history of LISA because, boy, it's been a ride. But it is now, as of hopefully next year, it will become a mission project of the European Space Agency with a mission date, and it may fly in 2034. So I always tell my students, please come to the old folks' home and tell me how it went, because I am really excited. It takes a long time to do all these things. I interviewed the head of LISA, and he said, yeah, that he has to retire next year. He says in Germany, it's iron. You retire at 65. He says if you win the Nobel Prize, you get 3 more years. So he says, I'm going to have to retire, but I am going to be there when they launch this, and I am going to. And he says, when he took over from the previous head, this guy's Karsten Dansman, the previous guy that he took over from Heinz Billing, when he handed over, Billing said to him, I am going to live until gravitational waves are detected. Remember 2015? He made it. He had to live to be over 100, but he died not long after they detected gravitational waves. So you've got to be patient in this field. Because my research is more about these big supermassive black holes, that's why I'm so excited. Thank you, Harold, for mentioning these. I am waiting till we detect two of those big boys crashing into each other. We think it will happen. We think as soon as they get one up there and it's working, we'll see them because there are so many of these things out there. Every galaxy has a supermassive black hole, and there are about 100 billion galaxies in the observable universe. So somewhere one of these things is going to be happening, and we're going to see it. So that would be the supermassive black holes, and that's why we're so excited, because there's been a lot of ups and downs. Peter Bender, the man who started the LISA project and who spent years lonely working out how to make this thing work, he started it in the mid-1970s. So he probably won't be around anymore when it flies. But you have to have this faith to keep on going. Okay, remind me the question.
About life?
Life, yes, okay. In a black hole. Okay, let me tell you about life in a black hole. Remember, we last left me being pulled apart, spaghettification. I brought up the supermassive black holes for a reason. In the supermassive black hole, that big of a black hole, the event horizon is actually not particularly close to the center. The event horizon is the point at which gravity gets big enough to pull light in. If the black hole is a lot of mass, that point is actually quite a ways out there. If we took one of the really biggest black holes, like 1 billion solar masses, in our solar system and put the center, the singularity where the sun is, it would reach to the Earth pretty much. So it would actually be a big boy in terms of the size of its event horizon. If I'm that far from the center, spaghettification isn't a problem anymore. So if you're going to approach a black hole, you've got to approach the big ones. It's a little counterintuitive. It's the small ones that'll kill you. They're deadly. Right? The big ones are like big slumbering whales. You can get close without getting killed. So I didn't say it because we hadn't gotten far enough yet, but when you told me to go down there, I said, okay, but I'm going down to a supermassive black hole. I'm not an idiot. Okay, so now I get to approach without spaghettification, but you are going to lose contact with me because when I go through the event horizon, I cannot send you a signal. There is no way to do so. What is life going to be like inside there? I don't promise that I'm really going to live because eventually I'll get close to the singularity and then I'll get pulled apart. But maybe I'm going to be alive for a while as I go down there. But now I've got to think about how strange it is in there. Think about what down looks like once you're inside the event horizon. You can't see anything in that direction because if there's anything down there to emit light, the light goes straight down. Remember, we discussed that in reality, in real relativity theory, the light doesn't even come up for a bit. It just gets sucked down. So I don't see anything ahead of me. Also, I have no capability to not go down. It doesn't matter how hard I fire my engines, I will go down. Right now in this room, we have a dimension that's like that dimension. Can anybody point me in the direction of that dimension? There is a dimension in this room right now. I am moving forward in that dimension, and I will never stop. And I cannot see ahead of me. I do not see anything ahead of me, and it is time. So, once you go through the event horizon of a black hole, down is the new time. That's now a time direction. It has all of the properties of a time direction. So our axes, which we're used to thinking of as immutable, we're used to thinking, boy, you can't interfere with space-time, right? The axes are fixed. No. Once you're inside the event horizon of a black hole, it all swung around. And what used to be a spatial direction, called down, is now forward in time. And up is now backward in time. And what used to be time is now a spatial direction. That's why in the movie Interstellar, he has him going in time. That part is not crazy. The crazy part is where he comes back out. I don't know how he does that. Okay. Yes?
So the black hole, everything in light is obscured inside, but not because it's obstructed from view, because it's in a different dimension that we can't see.
Yes. It's in a time dimension, right? Yeah, that's right. So it's become not a spatial dimension anymore. Yeah, that's right. Yeah. So just in the same way, we actually are, as you correctly point out, we already have one of those dimensions in this room, and we call it time. Yeah.
Crazy question, but is there a force that could be
Great question.
Like to lift a rocket into space?
A great question. And the answer is almost certainly no. Sadly, we'd love to have that. In the years after World War II, right, after Oppenheimer did his little party piece, every government in the world decided, I think I was going to fund some physicists. Anybody know any physicists? Because I've got some money for them, right? And the US Air Force started funding gravitational physics, which previously was a non-existent field, essentially. And they said, hey, are you a gravitational physicist? We've got some money for you. And the gravitational physicists, I've talked to the guys. I mean, I've talked to the guy who ran the US Air Force's gravitational physics department, for want of a better word, at Wright-Patterson Air Force Base in Ohio. And he said, yeah, they all used to figure that probably the Air Force was secretly hoping they were going to develop anti-gravity paint or something like that. But they knew that it was impossible. We do not know of any way, so here's the technical term we would use, we do not know of any way to screen gravity. I can screen an electromagnetic field for you. If I was going to do one of those fun, I didn't come at anything fun. Right? I'm not a proper physicist. I'm a theoretical physicist. I don't do fun things. I didn't come with one of those great Van de Graaff generators to make sparks. If you were a little nervous about the Van de Graaff generator, what would I do to protect you from the electric field? I would put you in a Faraday cage, right? If you're inside a car in a lightning storm, you're probably pretty safe because you're surrounded by metal. The lightning will follow the path of least resistance through the metal. Right? If you're in a plane, people are often worried about planes in a storm. But again, the metal will probably save you by taking the lightning around it. So you can screen the electromagnetic field. We don't know of anything that can screen gravitational forces. The whole Earth doesn't do it. So yes, there was middle of the 20th century people. There's a famous guy called Babson who was a wealthy industrialist who founded something called the Gravity Research Foundation because he wanted to come up with anti-gravity. And the physicists all said to him, listen, mate, it's not going to work, but listen, we can still use your money for good. We have never come up so far with anything that looks like it can screen gravity or do an anti-gravity effect, except one thing. So maybe we can close on this. Dark energy. We never did get to say a whole lot about dark matter, but I don't know that I might have run out of time for the dark matter. But the dark energy, it does do some anti-gravity. So what is so crazy about dark energy? Remember I said, think of dark energy like everybody's heard of zero-point energy. Any Incredibles fans out there? Einstein invented that too. He invented everything. Zero-point energy is like your ground state. That's when you're sleeping. That's your lowest state of energy. Many quantum mechanical systems, their ground state is not zero energy. It's some minimal amount of energy. They never get rid of that energy. That's hence the name zero-point energy. It could be that the vacuum has a zero-point energy. So that's called dark energy, and it's there everywhere in space. It's, however, a positive energy. It doesn't do any anti-gravity. What would we need for anti-gravity? We would need something that has negative mass, and we know of nothing that has negative mass. But Einstein's theory, this is how brilliant the guy was, Einstein's theory tells us that actually, unlike in Newton's theory, mass is not the only source of the gravitational field. Also, mass currents, moving mass. When I went down to the supermassive black hole, if that black hole was rotating, when I got near to it, I will find that it's impossible for me to not rotate with it. Again, think of space as like a river. It's like it's twirling the river around and I am carried around by the flow. It's impossible for me to not orbit the black hole. Okay, that's mass current, but again, the mass is always positive, so that's never anti-gravity. It turns out that the other source of a gravitational field is pressure or stresses. If I lean on the wall, turns out the pressure and stress I put on the wall actually has a little gravitational attraction pulling you in. However, pressure can be negative. Negative pressure is called tension. Positive pressure is what happens when you blow up the balloon and the pressure is pushing outward. Negative pressure is like an elastic band. When you stretch the elastic band, it's pulling back in. That's tension or negative pressure. Because pressure goes into the Einstein equations for gravity, when you have negative pressure, it actually has a little anti-gravity effect. Now, in all of the systems that we actually have around us, that's a puny effect that never does anything like real anti-gravity because, of course, the system itself has mass, which is pulling in. But if dark energy is a real thing, and it now seems that it is, it actually has negative pressure. which kind of makes sense in a way when you think about vacuum, because that's what it does, it sucks in. So that actually has negative pressure. So the dark energy is pushing everything, not pulling. And that's why we now know the universe is expanding. And for the 100 years that we believed in an expanding universe, everybody assumed that because gravity only pulls, that if the universe was expanding, then it was expanding at an ever slowing rate, because gravity would be pulling it back. They even calculated, theoretically, what they called the deceleration parameter of the universe, because it had to be decelerating, right? It had to be slowing. And then in the 90s, they measured the deceleration parameter, and they discovered it was negative. So the universe isn't slowing in its expansion, it's increasing. There has to be something pushing an anti-gravity thing. That something is dark energy. It's completely different from dark matter, incidentally. I didn't really get to explain what dark matter was, but that would be dark energy, and that would be a anti-gravity negative kind of thing. But it's kind of unique. There's really nothing else like it in the universe.
And is that what stopped, is that why it stopped collapsing?
So the universe, yes, in a bigger sense, for subtle reasons, it turns out that the expansion of the universe doesn't really have any effect on us here in this room. Right now, anyway, we're not expanding. The room isn't expanding. It's just the distance between galaxies that is expanding. But it is true that that means that there will never be any structures in the universe bigger than the clusters of galaxies we have now, because the universe is going to expand everything away before gravity has a chance to make any bigger structures. That's what we think currently.
Weird question. If you had a nice sized syringe and sufficient supply of dark energy, and you injected it into a black hole, could you just erase the black hole?
Good question. In principle, probably yes. Yeah. Bit difficult to say because hard to come up with one of those things about these calculations, of course. It turns out Einstein was great at thought experiments. It turns out in gravity, thought experiments are hard because you basically end up having to figure out what the properties of the syringe are, and then you quickly realize I couldn't build that syringe. But anyway, in principle, yes, I guess that'd probably be fair to say. Any other questions? Yes.
I was a little confused. So what's the difference between like the gravity that we experience and the gravitational waves you were talking about?
Okay, yeah, that's a great question. The best way to think about the gravitational wave is that it's very like the tidal force that we talked about. The difference between it, as a matter of fact, if we think about the Earth-Moon system, which is where we live, the Earth and the Moon are going around each other, which is exactly what the two black holes were doing when they generated the gravitational waves that we detected. So the question might be, okay, are we generating gravitational waves? And the answer would be, in principle, yes. In practice, no, because it's far too weak for us ever to detect. But the other way to think about it is that the tidal effect that we feel is basically like the incipient part of the gravitational wave going on. So when we have a gravitational wave that reaches us, it does a sort of a spaghettification, except that it's a wave, so it oscillates. So first, I get stretched and squeezed, so I got a diet, one looking svelte. And then in the next cycle of the wave, I get squished and fattened, and then I just keep wobbling back and forth like that. So it's just like a funny little oscillating tidal force that travels through space. It's a transverse wave, if anybody is familiar with that. A transverse wave is the kind of wave that vibrates opposite to the direction in which it's traveling. It's like water waves, right? They go across the surface of the water, but the motion of the wave is up and down. So the wave is coming through me like this, and then I'm squeezing and stretching in the opposite perpendicular directions to that. So that would be the simplest picture I can give of the gravitational wave. And the way to think about it is it's like a traveling tidal effect. Yeah. And the other way to think about it is it's a traveling distortion of space-time, and that's what the black hole is. I never said this because there just wasn't time, but the key point to remember about gravity is it not only changes time, remember I said that gravity distorts time, it also distorts space. That's the other thing that's bad news, dangerous about gravity. If the distortion is very strong, then that's not good. It also distorts space, so that close to a black hole, for instance, if I draw a triangle, it no longer has 180 degrees in its internal angles. pi is no longer 3.14159. It's got a completely different value. In a literal sense, the geometry changes. It's not Euclidean geometry anymore. It doesn't obey the rules that Euclid put in his famous book, The Elements of Geometry, 2,000 years ago. It obeys the rules of non-Euclidean geometry. Actually, it's not too hard to think about non-Euclidean geometry because we live on a curved surface. If I do geometry on the curved surface of the Earth, straight lines are not quite how they appear. I mentioned visiting Amsterdam recently. Where do you think I flew over on my way from Amsterdam to here? I flew over Greenland. Why did I fly over Greenland? Because the straightest path is shorter. It's curved in a curved manifold, right? So close to the black hole, you have curved space-time like that. And that's something that's also been proved true by Einstein's theory. So that's another big part of it that I should mention. So think of it as, if gravity can create curvature in space-time, you can think about them as being little hills and valleys. Then those little hills and valleys can travel in the same way that a wave on the sea is like a little hill and valley that's traveling along. So the common phrase about gravitational waves is that they are ripples on the curvature of space-time. Kind of a poetic way of thinking about it. Any other questions? I should probably let everybody go at some point. Physicists keeps people captive at library. Told they were going to be safe.
So, what do you think is the biggest room left for innovation, like after Einstein?
Oh, yes. Oh, yes. Physicists are inventive people, and there's lots of room. So, the singularity I mentioned, is it really a point? Is that possible? Quantum physicists would say, no, that's not possible. It must be jiggling back and forth. Just like the electrons and the neutrons jiggle. In quantum mechanics is the theory of jiggling. So they think the singularity must be jiggling a bit. Do we have a theory that can allow us to calculate that? Absolutely not. Would we like to have such a theory? We certainly would. Loads of people are working on it. We call it quantum gravity, right? It's the union of Einstein's gravitational theory with the quantum mechanics that govern nuclear weapons and all that kind of stuff. We have not succeeded in building that workable theory. So yes, such a theory would be sometimes called a unified field theory because we feel like the quantum theory's got all the other forces, electromagnetism, nuclear forces. We just need to bring the gravity into the fold. So that would be a unified field theory, or sometimes called a theory of everything. So yes, there's really, let me give you an example of how exciting it would be, right? Remember the dark energy, the 0-point energy of the vacuum? Well, I can calculate for you how big that dark energy should be from cosmological stuff. I'm not really the one who does it, but I can do a reasonable fist of it. Some people do it. We can calculate that out, and we get a nice small value for the amount of energy in the vacuum right now, which, of course, is everywhere, not just where there's pure vacuum. It's right here in this room. The dark energy is here. Okay, the particle physicists can do their quantum calculation. Oh, boy, can they. That's where 0-point energy comes from. They can do a calculation. Everybody knows that sometimes when you do a calculation, 2 kids in the class do a calculation, and they get an answer that doesn't agree. Maybe they're a little bit off, maybe a factor of 2. Maybe a factor of 10, and they're both worried, God, I don't want to get a D on this assignment. How far do you think us and the particle physicists are off? Anyone want to take a guess? What's the factor in it's something like 10 to the 40. It's a 1 with 40 zeros after it. Okay, they're wrong. Their answer is crap, it doesn't make any sense. Okay, but that would be, we would think we were done, right? If everything I had told you made sense, it would be that we could do our cosmological thing, measure what the dark energy must be to explain the accelerating expansion of the universe, and they could do their Feynman diagrams and work out what the vacuum energy must be. And if we agreed, we'd go, yeah, we've got it. We know what's going on with the universe, and we don't agree at all. So we need a theory that can do both calculations at once, and then hopefully get an answer that makes sense. Yeah, so that's where we stand. There's a lot to do. Think about taking up physics today. Thank you very much, guys.